All right, guys, domain. So I've got two parts I have to look at with the domain. All right, to start with, do we agree that that numerator, x squared minus 4, needs to be greater than or equal to 0?
Yes.
That's one thing I have to look at, right? I can't take the square root of a negative number. Then I also need to look at the denominator, because my denominator cannot equal 0. Remember this, the two parts? Put them together. Okay. First one, this is where you factor. And then what am I going to set up? Number line, good. So negative 2 and 2. What do we like to test? 0 lives in the middle. If I plug it in, I get a negative times a positive, which is negative. Are we okay with it alternating?
Yeah.
Okay. So this part, the ends plus the negative 2 and 2. Good with the first part. Okay, second part, x cannot equal what? 5, yes. So if I just visualize this, I'm not like doing a new number line test here. I'm just putting it all together on a number line. I know that part, right? The left end. And then I know from 2 to infinity, but 5 does not work. So that has to be an open circle. So when I write my answer, I go from negative infinity to negative 2 bracket, bracket 2 to 5 parenthesis, parenthesis, 5 to infinity. How do we do?
Good.
Okay, okay. If you have questions, let me know. You got it? Okay.
Is that negative 2 in the middle?
Negative 2 in the middle. Oh, like the 2 to 5?
Yeah.
Yeah, that's positive 2. All right, let's look at our graph. So this is skill 10. All right, x plus 3 quantity squared. I know that's a parabola, right? Okay, I'm also going to figure out the end point of the parabola, like where I need to stop. So I'm going to plug in this negative 1. What do I get when I plug in negative 1? 2 squared, which is 4. There we go. So negative 1, 4. I know I have a filled in dot. Are we okay with that? All right, if I look at the transformation of the parabola, x plus 3 quantity squared, where did it go? Which way? Left 3, right? Okay, that's where your vertex is. Does that fall in this x is less than or equal to negative 1? Yeah, so I'm going to plot my vertex over here at negative 3. You know it's everything from that first point we drew to the left. So you can just use what you know about a parabola and go, okay, over 1, up 1, up here, up here. Follow that with an arrow on the end because it's going to keep going. X values to the left. Did we get that first piece? Okay. Good start. All right, the middle piece, x plus 4, what is that a graph of?
Straight line.
Straight line. So can I just plug in the 2 endpoints and connect them?
Yeah.
Yes, we like those piecewise. When I plug in negative 1, what do I get?
3.
All right, negative 1, 3. Open dot, right? Okay, and then plug in 2, what do I get? 6. That sort of fits on my graph. 4, 5, 6. Sure, it's somewhere up here. Connect. There's my second piece. Hopefully that piece was the easy one for you. All right, last one. I've got a square root graph. Again, I'm plugging in the endpoint just so I know where it stops or starts, whichever way you want to think of it. When I plug in 2, what do I get? 3. Okay, so 2, 3. It's a filled in dot. Now, what shifts have happened to this square root graph? Okay, isn't that the point I just plotted? Yeah, it is. So I could just use what I know about square root graphs, like over 1, up 1, 4, 2, right? Like I know that shape and it's going to keep going that way. Trick people then. Hi.
It's literally right here.
I was trying to look at what we're doing. I'm not Mr. Grossman.
Did I overshoot? No, it's not that. It's 56, not 56. This is 50.
This is 65.
This is 65.
So keep going that way.
I know.
Oh. Just trying to help him out. So, all right. Back to our piecewise. Yeah. Yes. Yeah, you'll have like a coordinate grid to plot it on. So you won't be kind of like floating. Oh, it's hard on just regular paper. Yeah, I agree. That's why we've had a lot of printed notes for this one, because the graphing is just, it's hard without an actual grid. But the general idea of what's happening with the graph, do we have that? Whether or not it looks pretty. Okay. Lovely. All right, guys, then we're moving on to notes for today. Is anybody gone on Thursday because of AP testing or anything? I don't even know what tests are on Thursday. This is like in 2 weeks. As far as we know, we're all here. Yeah. The 8th? Yeah. Are you taking it?
Yes. I'm just trying to spell. It's supposed. Settle down.
So, Julian, are you missing or not?
I used to make sure. I'm actually not. I will email you.
Wait, what are you not sure about?
Because I need to get it. I think I wasn't sent an email for the AP testing, and I just need to make sure. But what I've gotten from the teachers, they can't respond to AP testing for that class.
Which class is it? Principals?
Yeah.
Okay. So if you're not here Monday, you can either take it on Thursday on the review day, or you take it during class on Wednesday and miss the notes and make those up.
What about like 4 months on Tuesday?
Probably. It's probably. Talk to me on Thursday, okay? So this is skill 10. We have skill 11. That's it. Cumulative, the one that can only help you. Yes. Why are you going to tank the cumulative? I don't understand. There's a lot I don't understand today, guys. All right. Okay, guys, we're talking about maximums and minimums. So an absolute max or an absolute min means it is the absolute highest or lowest a graph goes. So you don't need to write this part down. If you see a graph that looks like that, do you get how this is the absolute maximum?
Yeah.
Right? Like it can't ever go higher than that. If your graph looks like this, okay, that's a minimum, right? But is it a maximum, but is it the absolute maximum? Okay, so that one's called a relative max, or sometimes it's called a local maximum. It's still a maximum, but it's not the absolute. Same idea with minimums, right? What are we going to call this guy?
Absolute minimum.
Okay, what about relative min, right? Okay. That's a good chunk of the lesson for the day, guys. Yeah. All right, so let's do number 1 together. Is there an absolute max in this one?
Yes. No. With an absolute minimum.
Okay, so is there an absolute maximum? Okay, is infinity a defined like number?
I guess not.
It is not. So we would say none, or you can just like draw a line through it. There's not
Just
one.
gonna put
Okay.
absolute minimum.
Yeah, is there an absolute minimum?
-4.
Yes. Okay, we write it as what is the minimum, which is -3, at whatever x value it's happening at. So it looks like at x equals -4. That is just proper notation for calculus to get you in the habit of saying what the maximum or minimum is, which is the y value, and then where does it occur. Henry, phone. I think on Delta Math, they just ask you for what is the maximum or minimum. So that's just the y part of it. Like how high does it go or how low does it go? Okay. Do you see a relative maximum?
Yes.
Okay, what is it?
At 2, 1. So you do 2 at x equals 1.
Exactly. What is our relative minimum?
3 at 3.
1 at x equals 3. Sorry, -1 at x equals 3. Okay. Max and mins make sense?
Wait, why isn't the absolute minimum and the relative minimum the same? Because it's still in like third.
So you can have more than one relative minimum. So you could actually list the absolute also as a relative min. But what we're doing when we talk about a relative min is like if I look at just that part of the graph. Do you see the minimum?
Yeah.
Okay. That's what you're doing. It's like we're zooming in on one section. What is the max or min part of it? So like if that moves, you know, and you see this part of it, then you're like, okay, I have a minimum there. Okay. All right. Increasing, decreasing. You're going to list this with x values. Like you tell me over what x values is your graph increasing or decreasing. It looks a lot like domain. It's simpler in the fact that you don't have to figure out where it's an open parenthesis or where it's a closed bracket. We just use the soft parentheses for all of it. Because at that turning point, like where it goes from increasing to decreasing, at that exact point in the middle, that one's not increasing or decreasing. It's just where the changeover happens. So parentheses for everything. So do you guys agree that that section in blue is an increasing section?
Yes.
Okay, it's like reading from left to right, that's going uphill. So I would say increasing from -4 to 1. Okay, remember it's the x values. And then do you guys see there's another section of increasing?
It would be 3 to infinity.
Yes.
Would you put a u in the middle?
Yep. So then the downhill parts of the graph, I'm putting in red. So again, x values, the very left is -infinity. Up to -4, good. And then again from 1 to 3, yes.
1, 2, 3.
All right, try number 2 for me. We're not doing this one for sure. Okay, you can cross it out. But try number 2, I'll give you a minute here. Check in with your neighbor once you're done. Do you agree?
I've got a question.
Mm-hmm.
So if there's a point in the middle, like if you're doing the increase, whatever,
What does ink stand for?
increase.
Okay.
So if you're doing the increase model, would you go from negative infinity to negative 4, or would you go from negative infinity to negative 6 and then negative 6 and negative 4?
Does it stop increasing at -6?
That is a point.
There's a lot of points actually on this graph, right? Isn't there technically a point everywhere?
Yeah.
Okay.
Okay.
Yeah.
Thank you.
Only if it stops increasing would you stop your, like, what's happening with it, okay? All right, let's go through it. Is there an absolute max? No. Is there an absolute min? Okay. What is the relative max? Good. What is the relative min? Okay, where is it increasing? Good, and only one decreasing section from? Okay. Let's do...
Wait, so it's only absolute max or min if there's like two?
Or one, like a regular parabola has an absolute max or min.
Okay.
Do you know what I mean?
I'll know.
Like this is your absolute max.
Okay.
But there's no minimums on that. Okay. All right, we're only doing one more of these. Try number 4. Let's do that one. You can do the rest, but I think we're getting it, right? Okay. And those two are pretty repetitive compared to the ones up above. There's just some weird stuff in it that we're not addressing this year in pre-calc, so. Some of the stuff with the jumps and the open circles and all of that, so. Are we ready, guys?
I've got a question.
Okay.
What happens when the absolute minimum is at the same point?
Well, how about we go through it and see?
Okay.
Is there an absolute max?
No.
No. Okay. What is the absolute minimum? Yeah, it's 0, right? That's the lowest it ever goes, and it happens at 2 different x values. So you say at x equals plus or minus 4. You can list them separately, that's fine. Yeah. I like efficiency. Does that make sense? It's right, it's one minimum. You can't have 2 different minimums. They wouldn't both be the absolute min. But you can have the same minimum that occurs in 2 different places. All right, do we have a relative max? Yes. What does it look like? Do we have a relative minimum other than the two absolute minimums? No. Now, you could absolutely list those. That's fine. They are technically relative mins, but I don't need you to list extra minimums, okay? You don't have to repeat them. All right, where is it increasing from? 4 to infinity. Good. And decreasing. Yep. Okay. Doing okay with that stuff.
It's so okay.
Okay, turn the page. Okay, guys, we're going to jump around a little bit on this page. Let's do number 1 together. So on what intervals is r of t increasing? What would you say? 0 to 2. Anywhere else? No. Okay, where is it decreasing? 6 to 8. Okay. Now, this section here from 4 to 6, we didn't include anywhere. What is it called when it's a horizontal line? It's not increasing, it's not decreasing, it's... Anybody remember? It starts with a C.
Constant.
Yeah, constant. So if you see something like that, where it just stays the same y value, that's called constant. Okay. All right, now question 2. Minimums and maximums. Let's do the maximum first because it's easier. What is the maximum? Okay. Now, as far as minimums go, do you see anything that looks like maybe it's a minimum?
I mean, I guess you could. No.
Yeah, what about like, if the interval closes and that's the end point, does that look like a minimum?
Yes.
Okay, so I would include that. I'd say 0 at x equals 8, or at t equals 8, I guess is what I should be saying in this context. Sorry, guys. T.
So how do we know if it stops there?
Because the graph stops there. You have a closed interval graph here. Do you guys see another point that could be classified as a minimum? No, because that point, is it lower than any point around it?
No.
No, because it's the same as the points to the right of it. Do you see any other point that is lower than all the other points around it? What did you say, Maddie? Oh, okay. Julian?
0.
Okay. Just 0 or?
1,000.
Yeah, guys, it's an endpoint, so it's a little, sometimes the rules are different with endpoints. But looking at this graph, is that point lower than all the points that are in existence around it? Yes. So I would say 1,000 at t equals 0 also, okay? You'll get into a lot more details with open and closed intervals as far as maximums, minimums, increasing, decreasing, all that stuff in calculus, but general idea, and all we're going to do with it this year is that point lower than all the points around it? And it is, so that's a minimum. Okay? All right, we are not doing number 3, but let's do number 4. What does it mean to find r of 0? Yeah, look at the graph. What's the y value when your t is 0? So what do we get there? 1,000, yes. Because this graph is called r of t. Yep, that's the name of the function. Okay, the next one says r of 3. What's that going to be? 800, good. Okay, then find t when r of t equals 100. What is that asking you to do? Okay, clearly you know, yeah. 7.5. You're just going to go to your graph and say, okay, when it's 100, that looks like that happens right there. To me, that looks like a t-value of 7.5. Okay, so you're just you're just visually from the graph finding out what it is. Okay. Questions? Okay, we're skipping the last one on this page too, so turn the page. The notes look like a lot, but we get through them pretty quickly. All right, we're talking about discontinuity now. We've done a lot of these this year. You should have done all of them before this year, so let's just review them. So an infinite discontinuity, that's an asymptote. We did these when we graphed rational functions. Do you guys remember graphs that looked like this? Where you draw a vertical and a horizontal asymptote? Yes. So these happen when the denominator equals 0. So for part A here, that equation, where would our asymptote be on this? At 2. So you would say infinite, or you can say asymptote at x equals 2. That's the, usually name the type of discontinuity and the location of the discontinuity. Doing okay, guys?
Is that an answer?
Yeah. If I ask you about discontinuity, you tell me the type and the location. The type is infinite. You see this? Okay. The next type we're going to look at is removable. You guys usually call it whole. Okay, it's like on your graph, it looks like this. There's a little open circle on your graph. This comes from a factor canceling out. I always think of it as you remove the common factor, and that creates the whole. So if I factor here, I'd have x plus 3 times x minus 3 over x plus 3. I'm sorry, what? Okay. I didn't hear what you said. I thought I heard a 0, but that was all I heard. Okay. Cancel out your x plus 3.
That was right. Great.
So this time you would tell me there is a whole, or you could say removable, at what? What x value? Yep. Anybody remember, if you're graphing it, how to get the y part of the whole? Yeah, plug it into what's left. So no. So x plus 3 is the factor that gets canceled out, right? What makes that equal to 0? Like your factor that cancels. That's where it happens. Just like up here, right? The denominator, it's like you set that equal to 0 to find where the asymptote is. Same idea with those factors. Set them equal to 0 to find where the whole is.
It's
Okay.
the ones that you like cross out.
Yes. Yeah, not the one that's left. Tyler, question?
Yeah. How is it negative 3 though? We're not finding those goals on that.
Well, it'd be at -3, -6 if you were plotting it.
So like it's just not, it's never the scale. That's,
Oh, this graph has nothing to do with this equation.
oh,
They are not the same. Just like the one up here, those asymptotes didn't match up. It's like, here's a picture of what it looks like, and then here's algebraically what it looks like. Okay? So other than them not matching, are you okay? Okay. All right, let's look at a jump.
wait, actually.
Yeah.
So you get fx equals x minus 3. And then how does that become
What did you cancel out? What factor did you cancel out?
x plus 3?
And what makes that 0? Okay, that's why the whole is at x equals -3. It's the thing you canceled. What makes it 0?
Oh, so you just
That's what makes the whole. You remove that factor, so that's the one you said equal to 0. Okay. All right, third type is a jump. You most commonly see that with piecewise. We've graphed plenty of piecewise recently that had jumps in them. Okay. Okay. If we're looking for a jump algebraically, this is the x value we're going to be looking at, right? To see if they match. If your two pieces match, like you get the same y value, it's not a jump discontinuity. We've seen those graphs too, right? Like you graph one piece and it's an open circle. And then you go to graph the other piece and it like fills it in and does that. Not a jump, right? Because the ends matched. So the way we test that is I plug that -1 into each piece. So what is 2 times -1 plus 1? -1. And then I plug it into the other piece. What is -1 minus 4? -5. Do those two match? Okay, do not match means you have a jump. So a jump at what x value? What'd you say?
Is it at -1?
At -1. Yep, it's the x value that was in here that we were talking about. Okay.
You don't add any, like, the jump is 4, 3, 4, 6.
You just say whatever x value it's happening at. Yeah, you don't have to say how big the jump is or anything like that. Okay? Are we okay on the jump one? All right, let's try a couple. Let's do 1 and 2 together. All right, so I look at number 1. Is that a piecewise function? No, I probably don't have a jump happening then, okay? Is there any factor that can cancel out? Nope, so I do not have a hole in this one. Is there a denominator that could equal 0? Yes, so what do I have here? You can write asymptote or you can say infinite. At what x value? 7, okay.
Oh, the asymptote is a denominator.
Correct. All right, number 2. What type of discontinuity do you think we're looking at here? Jump. We're going to see, is there a jump? So what am I plugging in to check?
0.
0. What is 0 squared minus 1?
-1.
Okay. 2 times 0 squared plus 3 times 0 minus 1. -1. Okay, they match this time, right? What does that mean? No jump, no discontinuity, or you can just write this is continuous.
No. Still check.
All right, questions on 1 or 2? Okay, you guys try 3 and 4. They're trickier. See if you can find all of the discontinuities. You can have more than one discontinuity in a problem, okay? Talk to each other, work together if you need to. Yep. So you have 2 discontinuities. Yes.
That's why I thought if I was wait.
Yep, it is.
Can there be more than 2? Like just 2?
No, there could, I mean, in this one there is only 2, but potentially there could be, like you could have something that has multiple holes and multiple asymptotes. Or like in this one, you could have multiple jumps.
Oh,
I'm not saying it does or doesn't, but I'm saying it could.
just said it does.
But when there's multiple pieces like that, that's potentially what could happen. So guys, in number 3, there's 2 discontinuities. And number 4, there are 3 discontinuities. Did you find all 3?
Wait, I'm not there yet.
Okay. Julian?
So x squared minus 1, like on the denominator number 3, and I put it with the whole at x minus 1. So you count it.
There can be a hole at x minus 1. Look at all of these. It's a hole, like, so this infinite at x equals 7.
Sorry, infinite. No, I meant that's for the opposite. Sorry.
Infinite at x equals 2. Hole at x equal. It's always x equals something. It's not at x plus 5. It's not at x minus 2.
No. I meant that's not what I did before.
Okay.
I said
Say what you mean, okay?
X squared minus 1 is infinite at x.
Okay.
Is that correct?
Yes.
X squared minus 1 is also x plus 1, x minus 1.
Yeah, you have to factor on number 3, yes.
Would that be 2 factors?
No. Did you factor your numerator?
Oh, yeah, so one of them is a whole. So a whole can't be an asymptote.
Mm-mm. You've removed it. It is not there.
I also have a whole at x.
Yes. All right, guys, I'm going to factor number 3. So I see 2 factors that cancel. I know that creates a hole at x equals negative 1. And then, guys, do you see the factor left in the denominator? Yeah, what does that create? Yeah, infinite at x equals 1. Henry. Are we okay on 3? All right, 4. Lots of things going on in 4. So we have multiple places to check for a jump. I have to check these 2 with a 2, okay? And then I have to check these 2 with a negative 2. So when I plug a 2 into this top one, I get 2 plus 2 over 2 minus 3, that's negative 4. when I plug 2 in here, do I get -4? No, okay. So I have a jump at x equals 2 for sure. All right, then I plug in -2. So 3 times -2, so I get -6. Is there any way I'm getting -6 out of the absolute value?
No.
No, so I know I also have a jump at -2. Did you guys find the third discontinuity? Yeah. Yep, so infinite at x equals 3. Now, just because that top piece had a fraction didn't mean we'd have an infinite. It being at x equals 3 and then the interval including that, that's what says we have an asymptote there for sure. Right, so what I'm talking about, this x is greater than or equal to 2. The 3 falls in there, right? So that's why, yes, we have this infinite. If this had said like x is less than 0, you wouldn't actually ever see the asymptote. That make sense? Questions? So you can have lots of types of discontinuities all at once. Tyler, you okay?
It's not 3 just because it's not 3.
It's 3 because that's what would make the 0.
Yeah.
And then 3 is included in this, so that's why I included it.
If it's not included, don't pay it.
Right. Yep. Because you wouldn't actually graph it in that piecewise, so don't have to worry about it. All right, the last thing is end behavior. We've done this year. You did it in Algebra 2. You talked about like as x approaches infinity, y approaches, like that's the notation you used to use. You guys remember like odd functions, positive, negative, even functions, all that's what we're talking about here. So let's just go down and try these. But we're going to focus on using limit notation. So the way you write that, the limit of f of x as x approaches infinity equals, so let's think about the first one here. Which term do I look at out of this f of x function? Yeah, 2x to the 5th, right? That's the only thing I need to pay attention to. It's odd and positive, so I'm visualizing that little graph. Odd and positive. So as x approaches infinity, what is your graph doing? Infinity. And then we're also going to write limit of f of x as x approaches negative infinity. What would you tell me for that one? Negative infinity. Okay.
How do we know it does?
What's the degree? Okay. What do all odd functions look like? Yeah, weird stuff can happen in the middle. Like it doesn't matter. It could have a whole bunch of things like that, but you know the ends. Yeah. Because what does it always do if it's even?
Parabola. No, I mean, yeah, but no. Stays, goes in.
Yeah, a parabola, right? That is what you visualize.
Yeah, but I was saying it's not always a parabola.
I don't care what happens in the middle. All I care about are the ends. That's the whole point of end behavior, okay? All right, so number 2 down here. Which term am I looking at?
No, it's not.
I know, it's tricky. -4. Yes. It's mean that it's written out of order, so.
It's not written.
Even degree, negative leading coefficient. So what is that graph doing? Yep, both are pointing down, right? These take longer to write the limit notation than it does to actually think about and answer the question. So you have to write limit of f of x as x approaches infinity. We said that's negative infinity. And then limit of f of x as x approaches negative infinity is also negative infinity. Well, are both ends going down?
Yes.
Then there you go. All right, you guys try 3 and 4. Write the notation, the limit notation here. All right, so for number 3, I look at the x to the 4th. What are both ends doing? Yep,
Being
both
related to math.
going up. Julian, what?
Also,
And did we use the right notation, guys? So this one, I care about the negative 2x to the 5th. So limit of f of x as x approaches infinity, what is that? And then the other one, yes. Okay. Easy enough, right? You're familiar with that? Okay, just different notation. All right, guys, I'm going to give you the rest of the time to work on your delta math. So please start on the 10.3 delta math. I'll be checking in on you, seeing how you're doing. Oh dear. Thank you, Billy.